Okay, we're going to do converting between bases part 2. Before you look at this one, you probably should make sure you understand converting from bases part 1, which was these 2 bullet points, converting from a base 2, 8, or 16 number into decimal, and converting from binary into octal or hexadecimal. So what I'll do now is, first we'll do converting from octal and hex to binary. That's easy. And then we'll do converting from decimal to these other ones. So let's say that we have an octal number. I'll have hex here as something and binary. So if we have an octal number, the digits in octal go 0 up to 7, so I could have something like 5, 6, 2. Okay, so the rule from going octal to binary is that each digit in octal is worth 3 bits in binary. So I have to write 2 as a binary number. Just going to write it down. 1, 0. Now you can check that that's correct. This would be the 1's place. This would be the 2's place. 1, 0 in binary is 2. But the rule is that this 2 is supposed to give 3 bits. So I have to add an extra 0. I'll just draw a box around it because that's 1 octal digit. Now we would go on to this 6. So what is 6 in binary? 1, 1, 0, we have a 1 in the 4's place, a 1 in the 2's place. That is 6. Then we would move on to 5. What is that in binary? 1, 0, 1. You have a 1 in the 4's place and a 1 in the 1's place. 4 plus 1 is 5. So that's it. To go from octal to binary, you take each digit and just write it as a 3-bit number, and if you don't need all 3 bits, then you put zeros. Let's try hex. So we'll do a number like F1, 8 as a hex number. So the rule for going from hex to binary is that each digit is 4 bits. So we start with the 8 and write that as a binary number, and I'll write down 1, 0, 0, 0. That is the answer. Now you can check. This is the 1's place, 2's place, 4, and 8. So 1, 0, 0, 0 is the binary value for 8. Now we would go to the next hex digit, which is 1. 1 in binary is just 1. But for this to work out, we need to use 4 bits, which means we add some leading zeros. So that would be the contribution of converting from this middle digit. And then we have F, and F is worth 15. F is the digit in hex for the number 15. And you should remember that 15 in binary is just 4 ones. Okay, so octal to binary is each digit gives 3 bits, and hex to binary is each digit gives 4 bits. And that is why hexadecimal and octal are important for programming, because everything in programming in the end in the computer ends up as bits in binary. And if we look at the actual data, the actual stuff that's on the hard drive or in the memory, it ends up being bits. And if we group them 3 or 4 at a time, then we'd be looking at octal or hex numbers. Okay. Now, the last thing that we want to be able to do is to convert from decimal into these bases. Start with a decimal number. And first we'll go to binary. Let's start with something easy like 4. So what is 4 as a binary number? So for the small numbers, you can guess and check. 110 or 100 is a 1 in the 4's place, a 0 in the 2's place, a 0 in the 1's place. What about 5? That would be 1 more, 101. How about 7? That would be 2 more, so if we add 2, that's the 2's place there, we'd get 111. Okay, so you could do a guess and check method. Another method to do is, let's say we have a number like 40. So if you look at the what you end up doing with these 1s and 0s, you have a 1's bit, you have a 2's bit, you have a 4's bit. Those are all powers of 2. And so what your number ends up being, say this number 40, we end up writing it as a sum of powers of 2. So if we want to write 40 as a sum of different powers of 2, there's only one way to do that, and it is 32 plus 8. Those are powers of 2, and that's the only way to write 40 as a sum of different powers of 2. Now, if you know that 40 is the sum of these powers of 2, then this is 1 times 32 plus 0 times 16 plus 1 times 8 plus 0 times 4 plus 0 times 2 plus 0 times 1. Okay, and this here is what we would get if we were writing out, let's see, the numbers that I used here. 0, 0, 0, 1, 0, 1. So in binary, 1, 0, 1, 0, 0, 0. Okay, so if you take your number, you write it as a sum of powers of 2, those are going to be your 1 bits. Those are going to be the things that are going to be 1 in binary, and any powers of 2 that are missing are going to be zeros. Let's try another one like that. For small numbers, you can sort of do this in your head. Let's say we have the number 90. You probably want to remember the powers of 2. 1, 2, 4, 8, 16, 32, 64, 128. If we start writing them out and we get to a number that's higher than what we're looking for here, then that's enough. So 90 is going to be equal to 64 plus something. If you take 64 out of 90, what's left is 26. So we're going to have in terms of the ones that we're using here, we're going to have a 1 on 64. We use that. We're not going to use the 32. We're going to have 26 left over. We are going to use the 16. So we'd have 16. 64 plus 16, that puts us up to 80. We have 10 left that we need to get, and we would get that with 8 and 2. So if you write a 90 as a sum of different powers of 2, it's 64 plus 16 plus 8 plus 2. And if we're looking at the powers of 2 that we use there, we would have the binary right here. So this would be 1, 0, 1, 1, 0, 1, 0. Okay, so that's one method to convert decimal to binary. So we'll do another method to convert between decimal and binary. And so I'm going to put my decimal number, say 90. And this is going to be a different, an algorithm that's easier to do on paper, but is not necessarily what you would come up with on your own. But we'll get the same answer. So I'm going to keep track of a couple different things here. So there's my number. I'm going to keep track of if I divide by 2, what do I get? And what's the remainder? And we'll see what we get in the end. Okay, so what is 90 divided by 2? 45. The remainder is 0. Okay, and then I'm going to take this number here and I'm going to use that over here. So what I'm going to do is I'm going to repeatedly take whatever number I have here, divide it by 2, and look at the remainder, and then see what I get at the end. Okay, so what is 45 divided by 2? I'm going to keep a remainder. There will be a remainder of 1 because it's odd. And the divide by 2 part is 22. Okay, now I'm going to take my 22, put it here. What is 22 divided by 2? 11, with a remainder of 0. Now 11 divided by 2 is 5, with a remainder of 1. 5. Now divided by 2 is 2, with a remainder of 1. 2 divided by 2 is 1, with a remainder of 0. And last of all, we have 1 divided by 2 goes in 0 times, with a remainder of 1. Now if I take this number here and write it from bottom to top, 1, 0, 1, 1, 0, 1, 0. So that's this 1 goes there, and this 0 goes here, and that actually turns out to be my binary value. And you can believe a little bit where I started was at 90, and the first thing I wrote down was the remainder if you divide by 2. That's a 0. 90 is an even number, and it does turn out that in binary, any even number does have a 0 there. You could write down formulas to verify that this algorithm is correct. I'm not going to do that. So the algorithm is, we're talking about base 2 here. We look at the remainder when dividing by 2, and we divide by 2, and we repeat. So that's just a summary to try and jog your memory, but this is what we did here. And now we're going to do it in, this actually works for any base. So the reason to do this is it works for any base and it's doable on paper. And this is, it's a good algorithm for the computer as well. So I'm going to do this in base 8 now. If you're not quite comfortable yet, then you should do another example on your own. So you would look at, so you do divide by 2, and you do the remainder. Maybe do something like, I don't know, 81, take an odd number. And then what you should end up getting is the binary for 81 from bottom to top. So if you look at 81 here, one zero one zero 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 one. So you should get 1010001 if you do it correctly. Okay, so you probably want to do another example or two like that. You can check yourself with Google. I want to do this with base 8. So I'll start with a decimal number. Go ahead and start with 81. So I want to do, instead of 2s, I want to do 8s. Okay, so 81 divided by 8. There's a remainder of 1, and it went in 10 times. And then I take that number. I want to look at 10 now. 10 divided by 8. There's a remainder of 2, and it went in once. Now 1 does not divide 8 at all, and there's a remainder of 1. So if this works out, then 121 in base 8 should be equal to 81. And you can check this now. This 1 is the ones place, so that's just 1. This 2 here is the 8th place, 2 times 8. This 1 here is 1 times 8 squared. So that, and we add all those up. So we have 64 here. Then 2 times 8 is 16. That's 80. Plus 1 is 81. You can do another example. Go ahead and do one more. Why don't we do, say, 102. Okay, 102 divided by 8. You might have to do that on a calculator or something. Let's see, so 102 divided by 8. That's going to be, I believe, a remainder of 6. And it goes in 12 times. 12 times 8 is 96. Okay, so then we would take 12 as the next thing to look at here. 12 divided by 8 only goes in 1 time and has a remainder of 4. And then we have just the 1 left over. It doesn't divide 8 at all and has a remainder of 1. So this should be 146. In base 8 should be equal to 102 in base 10. You can check this. This is, the ones place is 6. 4 would be multiplied by 8 to convert back to decimal, and the 1 would be multiplied by 64. That should work out. 64 plus 32 plus 6. Okay, now we can do the same thing to convert from decimal to base 16. So now we're going to do, instead of 8s, we're going to do 16. We'll go ahead and do the 102, the same number. Okay, 102 divided by 16. We get the same remainder, it's 6. So 96 is 6 times 16. Alright, and then we would take the 6 as the next number, divide by 16, we get 0 with a remainder of 6. So it should be the case that 66 in base 16 is 102 in decimal. So 6 times 16 plus 6. Let's try another one. Okay, let's go with 201. Alright, 201 divided by 16. We're going to ask Google for that, so I don't make a mistake. Okay, so that goes in 12 times, and the remainder is, you have to do now, we get a remainder of 9. Okay, so then we have 12 here. 12 divided by 16 goes in 0 times, and there's a remainder of 12. We want each of these things here to be a digit, a hexadecimal digit. So 9 is fine, that's okay. 12 is not a hexadecimal digit. We have to use our extra ones. So we had A, B, C, D, E, F. A is 10, B is worth 11, C is 12, D is 13, E is 14, F is 15. So this in hex we write as C9. If we ask Google to convert 201 decimal to hex, it should say C9. Alright, so now we have our algorithms for converting from decimal to these bases. If you like any one of these bases, I'll put a note here. Note, if you like binary the best, then you can convert always to binary. Example, to do base 10 to base 16, you could do base 10, base 2, and then base 2 to base 16. Okay, so that's just a note. So for this one here, for example, we could have taken 201 and written that as a binary number. And then once we have a binary number, we could go to base 16 by doing the trick of 4 bits at a time gives 1 hex digit. So you should quiz yourself on these by writing down a number, trying out the algorithm, seeing what you get, and checking it by asking Google or a converter calculator.